Do I have a higher probability of getting kicked off of YouTube if we play Justin Bieber? Okay. For your thing yesterday, just use it. It's so sometimes assessments can just be information to you. Just use it as either I know how to do it, or if I don't know how to do it, I need to learn how to do it. I need to go back and do some homework, watch some videos, get some help. If it matters to you, those points, you can retake it on Thursday during resource. I kicked out the freshmen because we're having a Make-A-Wish meeting. So I have like tons of open space. I thought that'd be like a good day for you guys to come in if you want to retake it. Just for like mind management, because it's a lot of work to constantly be regrading everything. You're just going to print it off yourself. I posted in Schoology, print out the one you want to retake, bring it Thursday to resource, and just sit in the back and retake it. I'm not going to do the thing of like, you only have to redo the ones you got wrong, because that's just like an added layer of me thinking about it. So for a selfish reason, you're just going to retake the whole thing. For you, though, that's good for you to try it again and see if you can do it now. Okay, so today's Tuesday. You have until Thursday to learn how to do it if those points matter to you. I don't think statistically they are going to matter in the long run. We have like 1,000 points for all of the semester, so those 1 to 5 points aren't going to make a difference. But if it matters to you, because I know it does, you're welcome to retake it. For K units, this is the most common thing that we missed on that thing, was when we have a rate equation, our rate is in molarity per second. Our concentrations are in molarity. So I don't know why this is kind of a tricky concept, but when we do our math, we're actually taking those units with us. So we're taking our rate and we're dividing both sides by molarity squared and molarity to the 1 power. So tops of fractions, even if it's a top, is going to cancel a bottom. So I'm left with the seconds on the bottom. It doesn't matter that it's a top bottom, it's still on a bottom. When we bring it to the top, it becomes negative, and then m to the 2nd power. So if anything is to the 0 power, just like algebra, it means 1. So one of my m's cancels with one of my m's, and m to the 0 is 1. So all I'm left is a per second. PER means like -1. And then if our rate law is 2nd order in A and 1st order, it's not wrong if you write a 1, you just don't have to write a 1. And I doubled A, but B stayed the same. 2 to the 2nd power is 4, so my rate is going to be quadrupled. Sometimes these are just like multiple choice questions. Those are easy points, like 2 squared is 4, we can get that point. We only have to get to 55 points, so, okay? Don't forget, quick turnaround tomorrow is Form B on 8 and 9. It's an easy unit, you guys don't have that much to do, so we're going to handle that tomorrow. Today, we are almost going to finish learning this unit, which is why I'm like holding you accountable to that stuff, because like we are moving on. The next 3.5 units are about 3 to 4 times harder than this unit. So you gotta be able, equilibrium is a huge concept. It includes acids, bases, precipitation, all this stuff. So if you're struggling to keep up, then we need to maybe make like some more formal appointments or whatever, just to kind of give you a heads up on what's coming your way. Okay? Let's get out notes. We haven't in a long time. You gotta find this page, okay? Ready? Go. Okay. Way back on like day 1, we talked a little bit about the collision model. We didn't call it that, but remember, in order for a molecule to react with another molecule, they have to collide. So we've been drawing collisions as like stars as they collide on walls of the container, but because they're moving like molecule hands, they are going to run into each other. And when they run into each other, their electron clouds overlap. So that's like the sigma and pi bond thing. So if the electron clouds overlap, then we're going to have some exchange, some sharing, new bonds are going to be formed, and that's called a reaction, okay? So if I increase my temperature, I'm going to increase my kinetic energy, right? The words are, if I increase my temperature, I'm increasing my kinetic energy. They're the same thing. But it makes my rate faster because it gives molecules more energy. So this is going to increase my rate, the rate, of the reaction molecules collide with more energy. And frequency. Words. They collide with more energy and with more frequency. If they have higher kinetic energy, they're moving faster, they have more energy. Okay? The collision model is really based off of the kinetic molecular theory, which we did in gas laws. Remember, I was like teaching you the words. I'm like, make sure you're using the words, bless you, of the kinetic molecular theory. Okay? The collision model says three things. In order for a reaction to take place, three things. One, molecules must collide. They have to run into each other, otherwise nothing's going to happen. Two, in the correct orientation. That's where our colors are going to come in today. We're going to draw some pictures. And three, words. With enough energy to overcome vocab, activation energy. With enough energy to overcome activation energy. Okay? So let's talk about orientation. We get it. Molecules have to collide, but they have to collide in the correct orientation. Okay? I'm going to draw molecules in specific order, in a specific color. So if it's like hard for you to like look up and draw and try to match me, use your bad buddy, scoot to desk, be like, okay, what is she drawing? How do you do it? Try not to like get frustrated over which color goes where. I'm going to just use my regular red, blue, green. These are completely made up. There's no such thing as a green atom. It could be anything. I'm just using color to show orientation. So if I had a green atom, and he's hanging out doing a bunch of colliding with things, and he collides with a green, blue, red. I'm making it like a bench shape for no reason other than just to show it's like a molecule. So they're all hanging out, they're all having their kinetic energy. If the green happens to collide, star is usually our sign for collide, with the green on that guy, then I have a successful reaction, a successful collision. I make a new green-green, and I have a blue-red left over. Orientation for this like pretend example is green running into green. Green running into green is going to make a green-green and a blue-red. That's a reaction. But if I have my green, that's not cool. If I have my green and it's hanging out colliding with my green, but I'm going to draw it upside down. Green, blue, red. And instead of running into colliding with green, it runs into collides with red instead. Nothing's going to happen. It's going to bounce back. No reaction.
The same element, it's just like two things that can react.
I'm like trying to like, it could be like making a diatomic. Like it doesn't have to be. They're nothing specific. I'm just showing that the reaction is supposed to form a green-green, whatever green is. And if green doesn't run into green, it's not going to do that. In your head, though, if you wanted to, like, to me, like when I was drawing, I'm like, oh, it's like hydrogen and water, and it runs and makes this diatomic hydrogen. Like whatever you want to do to show. Orientation though, it's rare. Like what are the chances that of all the ways these can be flipped around, that green's going to run into green? Okay, they're constantly doing this. Most of the time they're doing incorrect. They're not forming a reaction. The faster they're moving, the higher kinetic energy, the more collisions they are, and it just makes it faster because they're running into green just more often. When the music starts, when Justin sings to you, please tell somebody next to you about what's correct and incorrect orientation and what it means, how it works. Orientation might be a new word. Ready, go. High voice, Justin. Okay, I'm going to make a big assumption, which is bad teaching, that you've played mini golf, and if you haven't played mini golf, that you've seen somebody play mini golf, or at least you're familiar with mini golf. But usually in mini golf, one of the holes, at least one of them has like this hill on it, right? And you have to hit the golf ball with enough energy to at least make it over the hill. Like if you don't hit it with enough energy, it just like rolls back. And it's kind of like, you don't want to hit it with too much because then it goes into the water. So like you got to make it just right. The activation energy is like this mini golf hill. We're going to draw a graph. We're going to go back to our energy graph, which is the exothermic endothermic graph. So we have time and we have energy. I'm going to make an exothermic graph for no real reason, just because that's what I'm picking. An exothermic graph means my final energy is less than my initial energy, because some energy was lost to the surroundings, from the system to the surroundings. So this is my initial, this is my final, this is going to be a negative delta E, we call that exothermic or exergonic, leaves the system to the surroundings. Something new, we have a hump in it. This hump is called the activation energy of activation. That's our mini golf hump. When molecules collide, even if they're in the right orientation, if they don't have enough energy to get over that mini golf hump, no reaction. Okay? So this here at the top of our mini golf hump is something called the activated complex. It's an actual molecule. It's a reaction. Sometimes, you guys, they call it the transition state. So I'm going to roll. It's like a green-green. Okay? So this size of this mini golf hill is dependent on a whole bunch of things. But the higher it is, the harder it is for something to react. To our eyeballs, it looks like it's a slow reaction. because they're running into each other, like no doubt they're running into each other. And they're probably running into each other in the right orientation just because they're all over the place. But if this hill is like super high, like way up here to our eyeballs, it's like, well, it's not really doing anything. Our reaction on Thursday is on purpose very slow. And it's on purpose very slow because I need to give you time to like put it in the cuvette and do like some things to it. But it has a high activation energy, and then the concentration of something is really, really low. So the chances of them colliding I kept really low. Orientation I can't help. Activation energy is really high, but that like gives you time to get it in the machine so you can start reading data, okay? So when the music starts, can you just point out the points of the graph, remind each other like what exothermic and endothermic is? Ready, go. Thank you so much. Energy of activation is always beginning to the top of the mini golf hill. Up here we have an activated complex or a transition state, but this is what we're adding to it now. That green activated complex, green ran into green and it made a green, is an actual thing. It's a molecule. So that means from here to there is a step. A reaction takes place, makes a green. But then here, all the way down, is another different reaction. It's a step. They're called elementary steps. We think of chemistry like this, but this is a way oversimplification of it. I know what I put in the beaker to mix, and I know what comes out of it, but there's a whole bunch of things that happen in between. They're colliding all over the place that are called elementary steps. If they're all in the same container, what's going to stop D from running into A? Nothing. That might make a DA. What's going to stop C from running into B or B from running into D? There's a whole bunch of actual things happening that scientists can predict, and they can only predict it because nobody can actually see at this point what's actually happening, and that's called a mechanism. A reaction mechanism is a prediction of the probable steps in a reaction. I can guess what they are, but my eyeballs can only see like beginning and end. My eyeballs don't see all those in between collisions. Okay? We're going to actually learn this in sample problems. So you're going to have to like page all the way to the back, and it's the very last page, and it looks like this. They're called elementary reactions. They're the steps in an overall reaction. How does it relate to rate? Some of those steps are so slow. They're so slow because they have a huge activation energy, or the orientation is tricky, or there's not a lot of them in there. But I can skip all of that poster stuff, all of like monkey and narwhal, in an elementary step. The only reason I can skip it is because it's prediction. We're just guessing. Okay? So what I want you to do with your availability when Justin sings to you, take a look at these elementary steps, and then take a look at how I can write a rate law just looking at the steps. How are they related? How do you figure it out? Ready, go. Okay, so when you have an elementary step, that means it's like, I don't know what's happening in between, but this is probably what's happening. All I have to do is take a look at the reactants to the left side, and it turns into my rate law. So if it's unimolecular, I just have the one reactant, rate equals K times concentration of A. If I have two reactants, it's called bimolecular. the number of them, the coefficient becomes the monkey, becomes the narwhal. Those are called rate orders. In your head, you're saying exponents. Sure. Those are called rate orders. Okay? So A times B, the rate order is still going to be 1 because there's 1 of each. If there are 3 of them, they are called termolecular. What you need to know about those is they are super rare and they are so slow. What are the chances that all 3 are going to collide at the same time? All 3 are not only going to collide, that they all collide in the correct orientation, and all 3 have enough energy to overcome activation energy. Like the chances of that happening is very low. Termoleculars are like, you look at it and nothing's happening. So slow. So in the words of the AP exam, it'll give you a clue, like it was really, really slow. The reason being the collision theory. Collision theory is that they have to collide. They have to collide in the correct orientation, and they have to collide with enough energy to overcome activation energy. That's just not going to happen all that fast. Okay, let's take a look at reacting mechanism problem. The balanced equation is here. This is the overall reaction. The overall reaction is the A plus B yields C plus D. This is, I put these 2 things in and I'm getting this. The experimentally determined rate law, they got the data table, they did the graphing, they figured out, just like you guys are going to do, is right here. Here's our rate law. I did all the math, and I put in all of my graphs, and I found out that NO2 is first order, and the F2 is first order. Okay? Suggested, we don't know for sure. The suggested steps are here. I think it's going to be 2 steps. I think the NO2 is going to run into an F2 and make these guys, and then the F is going to run in the NO2 and make this guy here. The question is always going to be, is this an acceptable mechanism? 2 things you have to look at. 1, does it add up to the overall reaction? We've played this game before. It's called Hess's Law, where we take our steps and we cancel things that are on opposite sides and then we add down. We're going to do that. Step 1 and step 2 should add to this overall reaction. So I'm looking for things to cancel. Remember, they have to be exact. So an F cancels an F. I think that's the only thing that cancels, right? So I'm going to add down 2 NO2s and an F2 still left, and then on my right side I have 2 NO2s. Does it add to my overall reaction? My overall reaction is right here. Does it match? Yeah. The answer to that question is yes. So only have the 2. Does the rate law match the rate up to and including the slow step? I'll show you what that means. Does the rate law match up to and including the slow step? Okay, I'm also going to assume today that you understand the concept of a relay. Okay, so running relay, swimming relay, whatever. A relay typically has 4 people on it. Your fastest person always goes last, your second fastest person goes first. When I did it, I always put the slowest second, and then the next fastest here. The point is, there's always going to be somebody who's the slowest, right? You're not all going to be exact. The slow step of the mechanism is called the rate determining step. The slowest person really determines how fast your relay is. If you got a fast, slow kid, your relay is going to be really good. But if you have like a really slow kid, your relay is not going to do all that well. It doesn't really matter how fast the fast kids are. If the slow kid's really slow, your relay is going to suck, right? The slow step is going to be labeled for you. You don't have to figure it out. Somewhere it's going to tell you which is the slow step. With the slow step, I can play this game. Up to and including. Up to means I get to stop after the slow step. If the slow step was second, then I'm going to have to add my steps together. Up to and including the slow step. If I only look at the slow step and I'm playing that game, rate equals K times the concentration of NO2, because that's my reactant, first power, first order, because there's only one of them, times the concentration of F2 to the first power, because there's only one of them. Does that match my experiment? Here's my experiment, here's my guess. That was this. This was this. Yes, they are the same. My experiment, my graphing, my data says I should have first order, first order. My guess, based on my slow kid, is that I should have first order, and it matches. Words. Yes, the mechanism is plausible. That means I guess my steps right, probably. Because it adds up and my rate law is right. Okay. The intermediate is the green at the top of the hill. The intermediate is the one that gets canceled. The intermediate is first seen as a product, then canceled. He's the green at the top of the mini golf hill. He doesn't stay long, but he's going to show up in my steps. The intermediate is F in this case. Okay, Justin's going to sing to you. You need to talk about what two things do I need to know to say yes, it's plausible or not, and then talk about what an intermediate is. Ready? Go. Chapter 14 worksheet. Guys, the worksheet packet. Okay, so judge yourself on whether you've done the work or not, so how you did yesterday and what you need to do before Monday. But you turn to the second to last page is number 9. That's where you're going to start today. So regardless if you've done the other stuff, start at number 9 today. I want you to start on it now and just get some like immediate practice on what we just talked about to help kind of solidify it. If you're starting at 9, you're going to finish through 12. So you're finishing the worksheet. It's just on what we did with the graphs and what's the intermediate, is it plausible, all that kind of stuff, okay? I'll post answers up here. Please work with somebody. I don't really want you to do it on your own in case you do something wrong. Tomorrow, all we have to learn is catalysts, and then once we're done with catalysts, we're done with everything. So then we have our lab on Thursday, review on Friday, quiz will be Monday. Okay? Ready, set,